I do without 15,
23.
Let's start with 15. That's a low one. 15 can get us, we think of it as a little warm-up problem.
Yep, that's what I was thinking.
Okay, great minds think alike. So 15 is not a difficult pattern to see, but it might be hard to draw. The first thing has a filled-in triangle, and then the next thing has a upside-down triangle in the middle of the filled-in one, and these guys are all filled in. So then the next thing, what are we going to do to these three filled-in triangles? Put in another upside-down one in all three of them. So we have this original setup, and then an upside-down triangle there, 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 and there, and then all of these get filled in. So if you're going to do the next one, unfortunately for you, how many upside-down triangles do you have to draw? 9, because each one of these filled-in triangles should now have an upside-down triangle in there instead. And this is actually has a special name. It's called a fractal. And this fractal has a particular, it's called Sierpinski's triangle, and it's famous for some different reasons. So that is stage 1, and then I forget what I'm supposed to do with this. Anywho, okay, so you're just supposed to take that and put 9 upside down triangles in there. Okay. All right. What else?
23.
23. Somebody say
22.
17 and 18. 17 and 18? Okay. 17 and 18 are good ones to do because they, oh good Lord, I am having a rough day all of a sudden. Because they relate to, there we go, what we're going to talk about today. And that is coming up with a formula for these patterns. So instead of just saying, okay, it goes up by 3 every time, being able to look and say, all right, this is the formula, so if you want to know what the 500th term is, you just plug 500 into the formula, and away you go. So let's take a look at this. The first term in this sequence would happen when n equals 1. So what do you get when you plug in 1 for n? 1, because 3 times 1 is 3, minus 2 is 1. Okay? Then you're going to plug in 2 for n, and you get 4, good, because 3 times 2 is 6, minus 2 is 4. And then if I plug in 3 for n, what do I get? 7. And so now you should be able to look at these answers right here and figure out what the next numbers are without plugging stuff in. What's it going up by each time? 3. So the next one will be, and then 13, okay? So we'll leave it at that. So that's the next answer. The answer is 1, 4, 7, 10, 13, going up by 3 each time. All right, number 18, they get us started on the pattern and then give us the formula. Bless you. This is a little bit trickier of a pattern, and so the formula is a little bit more tricky as well. What is it going up by from 1 to 3? 2. Okay, so this goes up 2. From 3 to 6 is 3. And from 6 to 10 is 4. Okay, so you could get the next 5 terms that way. What's it going to go up by next time? 5. So it will now be 15. And then it goes up by 6, which gives me 21. Goes up by 7, which gives me 28. Goes up by 8, which gives me 36. It goes up by 9, which gives me 45. Okay, so that's one way that you could do it. It's just by recognizing that you're adding one more every time through. Okay. The other thing that you can do, which like I said is something we're going to start working on today, is you can take this formula and figure it out by just plugging numbers into that. So they gave us the first, second, third, and fourth numbers in the pattern. So to get the fifth number in the pattern, I plug in 5 for n. What's 5 plus 1? 6. And then 6 times 5 is 30, and 30 divided by 2 makes 15. So you can see how those match up. So you should be able to get the same answers either way. Same thing if you plug in 6. 6 plus 1 makes 7. 7 times 6 is 10 half of 42 is 21. Okay, so whether you use the formula or whether you recognize the pattern is totally up to you. Okay? All right, where do we go from there? 23. All right, 23, they have this weird thing going on where they go, look, if you take 12 and square it, you get 144. If you take 21 and square that, you get 441. How are these things related? They're just opposite, flipped around. So I took the 12, flipped the digits, and got 21, and then my answer got flipped 2. Oh, just a coincidence, you think? Oh, no. Works for 13 also. 169, flip that around and make it 31 squared, you get 961. Wait, you say, perhaps that only works for 2-digit numbers. Oh, yeah? Well, how about this 3-digit number? 103 squared is 10,609. 301 squared is 9,601. Okay? So it looks like if you take a number and square it, if you flip the digits and square it, you'll get the flipped answer. Do you think that's true?
No.
No. Give me a counter example.
10.
Okay. 10
That was mine.
squared is 100. What's 10 if you flip the digits? 1. I'm going to write that as 0, 1, just because I'm annoying. And then if you square 0, 1, what do you get?
1 or 0,
It could be 0, 0, 1. So you could sort of argue that it might work for that.
That would work.
That's a little sketchy because of the zeros, but Mickey? What? Okay, let's try 18. You know what 18 squared is? I don't know what 18 squared is either, but this magic device that lives inside of my computer knows. 18 squared is, please talk to me, magic device.
I don't like those calculators. No, don't confuse.
You have offended the calculator.
Thanks a lot.
Whoa!
See, they're hard to use.
18 squared is 324. And so then I should be able to flip that and go 81 squared, and if this rule holds true, what should I get?
43.
Oh, too bad, it doesn't work. Yeah, so one counter example would be that 18 squared equals 324, but 81 squared does not equal 423. Okay? So that's what they're looking for you to do there. And again, the idea here is that inductive reasoning is a great tool, but you have to be careful with the assumptions that you make when you use it. And here's another example of that. If I start with 1 times 1, I get 1. If I go 11 times 11, I get 121. If I go 111 times 111, I get 1, 2, 3, 2, 1. If I go 1,111 times 1,111, I get 1, 2, whoops, 1, 2, I can't count, 3, 4, 3, 2, 1. Do you see the pattern?
Yes.
Yes. Counts up to a number and then turns around and goes back down. And the number that it counts up to matches the number of ones in the thing that we're multiplying. So, stands to reason if this pattern holds true, if I go 5 ones together, I should get 1, 2, 3, 4, 5, 4, 3, 2, 1. Okay? Yes? Do you like it? All right. So 1, 2, 3, 4, 5 ones times 1, 2, 3, 4, 5, 1, and I get, sure enough, 1, 1, 2, 3, 4, 5, 4, 3, 2, 1.
What about 10?
10 ones?
Go for
I was
it.
like
Okay.
10 kids.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Oh,
Instead of retyping that, I'm just going to say squared. And now the pattern falls apart because, like you said, you can't really have a 10 in the middle there because now you have a 2-digit number. So it would be 1, 2, 3, 4, 5, 6, 7, 9, and then it gets kind of screwed up. Okay? So the answer is, what would be the conjecture for the 6th line? So the conjecture for the 6th line would be that you would get this as your answer. Okay? Or is that on the 5th line? That's the 5th line. So the conjecture for the 6th line, 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5, 6 would be 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. Did anybody check that? Does that work? I think it does. I think it works all the way up to 10. And then the conjecture for the 10th line, we don't really know how you would write that because of the 10 in there. So I don't know what they want to put that. Okay?
Yeah.
All right, anything else? Going once. Going twice.
Are we over it?
Oh.
Okay, we please trade